And this screencast is about naming and drawing the organic family or class of ethers. Ethers contain this linking oxygen, which is often referred to as an alkoxy functional group. Okay, so they have the alkoxy functional group of a linking O between two different carbon chains. Okay, so naming ethers, drawing ethers, they're a little bit different with their IUPAC naming system than some of the others, because in a way, you kind of need to think of both the linking oxygen and the shortest carbon chain as kind of one collective functional group, and that would become the alkoxy substituent in a way. Okay, and then the way you name them then is you say alkoxy alkane. So basically the shortest one is the alkoxy group, and the longest carbon chain becomes the alkane group. So if we kind of go through and circle on these three, there's going to be your alkoxy group, there's going to be your alkoxy group, there's going to be your alkoxy group. It's not like they're always on the right hand side, it's just how it happened to be set up in my picture here. Okay. So we would name this first one here would just be methoxymethane. Okay, methoxymethane. This one would be also called methoxy, but we now have an ethane over there, so it's methoxyethane. And this one would be ethoxy propane. Okay, so you see how the shortest group always the shortest carbon chain also kind of gets to hang on to the linking oxygen in an ether, and that's how you name it. Okay, let's draw a few of these from the names. So once again, pause the video at any of these moments and try them for yourself first. It's probably your best strategy. But ethoxypentane, remember that this just means that the O goes with the smaller F. Okay, and then pentane is 5 carbons, toss 5 carbons on the other side. And if you're lazy like me, one stick will indicate the hydrogen. 2-methoxybutane. Interesting, we haven't seen this yet, but this is, if it's given a position for the alkoxy group, alkoxy functional group, that tells you that this is actually functioning more like an alkyl substituent. So if you just draw butane, a 4 carbon run off of carbon 2, we have a methoxy, so that's going to look something like this. Or I could draw it out. I've just kind of run out of space, so I'm condensing it a little bit there. All right, and then this one, 3-ethoxypentane. This is going to get kind of large, so let's draw a pent. Okay, then off of carbon 3, we're going to draw an ethoxy group. I'll try and draw the whole group out here if I can. Yes, so it could look something like that. We could also try and do this in a condensed structural formula so we don't have to write quite so much. Might look like that. What's it do? It goes to a carbon there, and then oh, it's almost like a little body there. All right, if we think a little bit about the physical properties of what are these things called again? Ethers. If we think about the physical properties of ethers, geez, write it here so I don't forget what I'm talking about. If they're small, like a lot of things, if they're really small, they're going to be more water soluble. If they are larger, they're going to be less water soluble. So a small one like this can be water soluble. Okay. Will it be able to hydrogen bond with water? You have to look it up and check that one out. When I Googled it, it says that yes, they can. I guess that's the same rationale as a carbonyl group being able to hydrogen bond. It's got an exposed oxygen and it can form a hydrogen bond with water, but they definitely cannot hydrogen bond with one another. All right, so they can hydrogen bond with water, but no hydrogen bonding between two ethers. The ether molecule is polar as well. It's a little bit, it may not look obviously polar, but one thing you have to remember is that if we draw the full Lewis structure, remember there's going to be a couple of lone pairs on that oxygen. And so the shape around that oxygen is actually going to be bent. So if we were trying to draw this a little bit more to reflect reality a little bit more, it might look a little bit more like this, right? With taking Vesper theory in mind, that we actually have kind of a bent or a V-shaped type shape. So it is polar. There would be some dipole-dipole interactions there. In general, like most of these, like most members of a homologous series of any organic family, the larger the molecule gets, the higher the melting point and boiling point would be. But that's because of dispersion force, London force, not because of dipole-dipole force. So the larger the molecule, the higher the melting point and boiling point. And then finally, I mentioned that if they're small, they're water soluble. Like, how small do they need to be? What happens is if they get too large, then they are no longer soluble in water. So I looked it up, and it says once they get larger than 3 carbons, they're non-soluble. So they're not soluble after 3 carbons, if greater than 3 carbons. Okay? That being said, if you wanted to compare an ether with a similar, which is right there, methoxymethane, with a similar sized alkane, like this guy, ethane, you would still find out that this one, the ether, had the higher melting point and boiling point, because it can still have dipole-dipole interactions with neighboring molecules, whereas the hydrocarbons would have nothing but dispersion forces or London forces. Okay, so these have only London dispersion forces. Hopefully you found this helpful.